Hello, everyone. Thank you very much for attending the session. We are going to do geometry today. I think it is the very first lesson in geometry. And we are going to start right from the fundamentals and go through them as quickly as possible before going on to the problems. So without much further ado, let me take you straight to my screen. Geometry starts with a lot of axioms. Axioms are self-evident truths. In other words, you know it's obvious, and we don't have to make any effort to prove them. For example, if you have got 2 points on a sheet of paper, you can draw exactly one straight line going through those 2 points. That's an axiom. Another axiom is that if you take a straight line and you have a point outside it, then through that point, you can draw exactly one line which is parallel to the given line. Okay, to explain that, like for instance, if you had a straight line, and you have a point outside it, take some point here like this, right? Maybe I better illustrate a point. Now through that point, you can draw a line which is parallel to this. In fact, you can draw exactly one line which is parallel. Parallel lines, we don't define parallel lines, but we say that they have the same direction, which is a kind of a loose way of saying things. So you can draw one line. It is possible to draw a line which is going through the point and parallel to it. Okay? And with parallel lines, there are several axioms. Here you can see 2 lines are parallel on the left-hand side of the screen. And you have a line which is cutting those 2 parallel lines. And a lot of nice things happen. You've got 4 angles formed at one line here. And you got another 4 angles formed here. So you have 4 angles here and 4 angles here. It looks as if there are 8 angles, but in fact, there are only 2 distinct angles, right? We're going to see why. Because before we do that, if you got 2 straight lines cutting each other, then these angles here are called vertically opposite angles. And this angle is opposite that angle. We call them vertically opposite angles. Vertically opposite angles are equal, right? And if we want to see why, suppose you got this is x and this is equal to y. So y is x equal to y. A very quick way of realizing it is that take one of those angles there, and you can see quickly that x plus z is 180 degrees because these 2 angles lie on a straight line, that one and that one. And likewise, y and z lie on a straight line, and y plus z is also 180 degrees. So you can make them 2 equal, and then when you cancel the z on both sides, you land up with x equals y. So these 2 angles are equal. They are called vertically opposite angles, and vertically opposite angles are actually equal. So in place of y, we can actually write x. All right. And here too, this is same as that. Okay. Now, if you take these 2 lines which are parallel, I think I said earlier on, although they look as if there are 8 angles here, in actual fact, there are only 2 angles. Let's see why. All right. Now, an axiom in geometry is that when you got parallel lines, then the z angles are equal. And let me explain what you mean by z angles. The z's can be quite distorted. Like for instance, this, there, that's a z. And the z angles are equal, which means the two angles which are formed by the z, that, so there's an angle formed there, and you go down and you go this way, there's a new angle formed, and those two angles are equal. So the z angles are equal. Of course, we saw that these vertically opposite angles are equal. So you can see there are only four angles. There are four equal angles straight away. Okay. And bearing that in mind, you have another z here like this, which is a kind of a deformed z, upside down z. It's what a child will write for a z. So if you call that y, and you go down, come down, you go down, then that's a z angle. And of course, since vertically opposite angles are equal, so you see, although there are 8 angles here, these angles are actually there are only 2 angles. Right. So these z angles are called alternate angles, and I think you know that. And so we just said that the alternate angles are equal, but we just saw now that if you look at this picture again, you will see that there is an F here. See? So there's an F. And if you look at the F, you got parallel lines. And the angles under the parallel lines, you can see there's the two parallel lines are equal. The angles under the parallel lines, that and that, they are equal. So those are called corresponding angles. All right. So parallel lines, you have alternate angles are equal, corresponding angles are equal. And if you look at the angle, there's a U there as well. If you take this, that, and that, then you have a U angle, like that. And those two U angles, you can see X and Y, right? When you add them, you'll get, as you can see, X plus Y, which is 180 degrees. So the U angles are supplementary. The sum of the U angles are always supplementary. Okay, so these are axioms. Then there is a theorem. The first theorem that you learn is that vertically angles are equal. Vertically opposite angles are equal, which I've just illustrated. And the next theorem that you learn is that if you take any triangle, and if you add the angles of a triangle, you get 180 degrees. The three angles of a triangle sum to 180 degrees. The angles are not equal to 180, but they add up to, they sum to, right? So now, for instance, in this diagram here, you want to prove, there's your blue triangle, you want to prove that the three angles of the triangle, which you can see in the picture, are X, Y, and Z. And we say that they are, when you add them up, you get 180 degrees. I got a question mark to say, why? How do you know that they add up to 180 degrees? It's quite easy to prove. If you take any point, like point one of the vertices of a triangle, like this one, and through that point, you draw a line which is parallel to this one here, then what happens is that you get a Z angle here. These angles are equal. And here you got another Z angle. And these two angles are equal. So when you make put the y there to show that they are equal. You can see x plus y plus z is actually all the angles which on the straight line. And you know that a straight line, if you add the angles on a straight line, you're going to get 180 degrees. So that is why x plus y plus z is 180 degrees. Okay, I'm going through all this very quickly. And you can see everything is very logical. There are a few axioms, and then you can make conclusions. Like we proved that these two angles are equal. And we proved that x plus y plus z is 180. You can verify by measurement, but that doesn't prove it, because you need to prove it for all possible triangles, no matter where you draw them. Right? And this is a random triangle we've drawn, and we've shown that the three angles sum up to 180 degrees. Okay, then the next theorem, which involves taking a side of a triangle and extending it. So if I take a side of a triangle and if I extend it, like in this triangle here, you got the three angles are x, y, and z. And if I extend it, then a new angle is formed, namely W, in this picture here. In fact, you can take any one of the sides and extend it in any direction. I could have extended it in that direction, or I could have extended this line in that direction, and so on. But each time you extend a line, you get a new angle that is formed, like in this case. And there is a result which says that the new angle that is formed is actually equal to the sum of the remaining two angles. When I say remaining two angles, this angle is right next to this. Don't worry about that one. You worry about the other two. There are three angles in a triangle. Take the other two. And the nice thing about it is that when you add these two angles, you're going to get this. So this is called an exterior angle because it's outside the triangle. So the exterior angle is equal to the sum, you're adding, of the interior opposite angles. Right? That's what you say here. These are called the interior angles, but they're opposite. They're not next to W. Okay, why is it true that W is equal to x plus y? The answer is very simple. I see that I haven't really proved it down here, but you can prove it. The reason for this is x plus y plus z, we saw just now, that's 180 degrees. And we also know that W plus Z, those two angles lie on a straight line. So W plus Z is also 180 degrees. And if you cancel the Z's, there you have it. X plus Y equals W, which is exactly what we said. X plus Y equals W. You notice I use algebraic symbols. And algebraic symbols makes geometry very easy, right? I know in school you'll put symbols here, A, B, C, and you'll say angle ABC plus angle BCA. All that is very complicated and it makes very difficult reading. But if you name angles with symbols, you can come to conclusions very, very quickly, like the way I have been doing here. So we have just proven that the exterior angle, an exterior angle of a triangle is equal to the interior opposite angle. I call this the flag theorem because what actually happens is I've got a flag here. You got a straight line and you got something like that, and something like that. And that's a flag, right? So the exterior angle is equal to the sum of these two corner angles. So the corner angles add up to the exterior angle. And you can put this in any direction. Wherever you see a flag, you must remember that the exterior angle is equal to the sum of the interior angle. That's a theorem in geometry. All right. And then another very important result is that if you've got two angles of a triangle equal, right? So on the left-hand side, I've got a triangle here, and I've got two angles equal. So when you got this x is x, that means these two angles are equal. A very important result, or a theorem in geometry, is that the sides opposite these angles. Now, you see, let me just stop here for a while. Every triangle I'm going through this rapidly because when you have the video, you can stop and think about what I am saying and, try to understand it. Now, every triangle has got six numbers associated with them, right? And the six numbers are the three angles and the three sides. Right? These are the three angles, A, B, C, and the three sides. We normally put a small a opposite the capital A, small b opposite the capital B, small c. So you have opposites. You have an angle and you have a side opposite it. So often it's nice to go work in pairs like that because an angle and the side opposite it. Angle, side opposite it. So they come in pairs. There are three pairs, the angle on the side, angle on the side, angle on the side. So here we are saying that if you've got a triangle with two angles equal, then the sides opposite these angles, that one, right? You can see it's there, is equal to the side opposite this angle. There it is. So you can see I've got two little strokes here, which means that these two sides are equal. I've got the same symbol on a side, I mean they are equal. So here you've got, if these angles are equal, then these sides are equal, the sides opposite the equal angles. Right, and I got a direction. It means that if you know this, you can immediately write down this. That's a theorem, immediately. And there is a converse. By converse, it means that if I know the result, if I know that the triangle, if the two sides are equal, right, does it mean that the angles opposite these equal sides are equal? Now you've got, there's a side, there's an angle opposite it, there it is, and you've got the side here, the angle opposite it, and you can see I've got the same x. So you can also say that if the sides, two sides are equal, then the angles opposite them are equal. So you have this direction like this. And sometimes what we do is, instead of writing two different diagrams, we simply put a double-edged arrow. I can put an arrow like that, which means that from this, I can conclude this, and from this, I can conclude that. So whether you got the angles equal or whether you got the sides equal, then it doesn't matter. Then the other result is true. So whenever you have a triangle with two angles equal or two sides equal, that triangle is given a special name. It's called an isosceles triangle. An isosceles triangle. Right? That means two sides of the triangle are equal. Now, it's quite possible that you have three sides equal, all three sides equal. In that case, when the three sides are equal, then you call that triangle, you give it a name, it's called equilateral. Equal. Lateral is the word for side. So equal sides. So you have all these are equal. That's what you call an equilateral triangle. And we just saw that because these two sides are equal, these two angles are equal. But now you've got these two sides equal here. So the angles opposite these equal sides, like x is opposite that one, and the one which is opposite that is there, these two. They are also equal. These two are equal because those two are equal. But now you have that the triangle, it's got three x's. But we know that when you add the three angles of a triangle, you'll get 180 degrees. Right? But that x plus x plus x is 3x. That's what algebra tells you. And if 3x is equal to 180 degrees, then x is 60. So this is a very important fact, that in an equilateral triangle, all the angles x are all equal to 60 degrees. So such a triangle is called an equilateral triangle. All right, so I've gone through the most important results that I plan to do very quickly, and it'll do you good to go over them and digest these results so that you can repeat them at any time, right? So please, these are theorems in geometry. The sum of the angles of a triangle is equal to 180 degrees. An exterior angle is equal to the sum of the two interior opposite angles. If two sides of a triangle are equal, then the angles opposite them are equal. And if two angles of a triangle are equal, the sides opposite them are equal. Alternate angles are equal. Corresponding angles are equal. Co-interior angles are supplementary. They add up to 180 degrees. So all these things, these are facts which we will use in the process of solving problems. And that is what I'm going to do now. Okay, some of these problems may not be the the kind of problems that you will do in school, right? They are a little bit more demanding because we are now doing Olympiad problems. All right, so what do you mean by a problem? A problem is something where you got a piece of information that are given. You may have a diagram, and you may have shown some parallel lines there. You may show some equal sides, or you may show some equal angles, and so on. So you are given certain pieces of information, and you're asked to prove something which you don't know, and you're asked to prove something and say, prove that. You have to show why such a statement is true. All right. So in this case here, if you look at this triangle, you can see I'm given that this angle here is 40 degrees, right? So we can name that angle. How do you name an angle? An angle is sitting between two straight lines. Right? Every angle is sitting between two straight lines. So you start from one end of one straight line, go through that angle, and go up to the end of the other straight line. And that way you will name your angle BAC. Start from here, go up to A, and come up to D. Or in this case here, you got BAD. I'm finishing off here. And it is given that angle BAD, you can write like that, or there's another way of writing it, which I use often. Sorry, BAD. That's bad. Make an error here. Okay, so in this case, it's given that this is 40 degrees. This angle here is 40 degrees. But you're also given some other things. You're given that AB is equal to AC. AB equals AC. In other words, triangle ABC is isosceles. Two sides are equal. You're also given that AD, here it is, AD equals AE. So if you look at the picture now, AD equals AE, so which means that triangle ADE is also isosceles. But you are not given any other angle. You're just given that that is 40 degrees, and you are asked to calculate X. That is really the problem. I haven't written it down, but the prove or calculate X. Okay, so that is the problem. How do you calculate this little angle here? Okay, now you would do well by stopping here and trying to prove it yourself. All right, close everything and try to prove it yourself. And after you have tried, then you can come back and look at what I'm doing. Now, unfortunately, we don't have time to give you to do that, but I'm going to give you the solution in all these cases. Okay, so let's go. We're going to try to calculate angle X, and I'm going to do it down here. Okay, now, where do we start? We know that AD equals AE. So the conclusion from that is that the angle opposite AD in this triangle here, let's call it Z, don't give it the same name as X, and it's equal to AE, so the angle opposite AE in the same triangle is that one. Those two angles are equal. Okay. All right. And then we also have that AB is equal to AC. So the large triangle is isosceles. But we don't know the sizes of B and C. But if you look carefully here, you will see a flag here. Can you see? Can you see the flag? So what does it mean? It means that you can use the exterior angle theorem, which we said earlier on, to say that the exterior angle, Z, right, and the two corner angles of this flag here, one is X and the other is angle C. All right. Now, that's useful because now I can calculate angle C is equal to Z minus X. If you make angle C the subject of this formula, angle C, you bring the X to the other side, you'll have C all alone. So angle C, now we know what it is. But we know that AB equals AC. So if this angle is Z minus X, as we have just seen, this angle here is also Z minus X. See? All right, so how do you find? So how do you find X? So maybe well, if you look at you got another flag here. See, if you start from C, go up there and come down there. This flag includes the 40 degrees. So that's nice. You can go up, come down, come down. So this corner angle, which is 40 degrees, plus the other angle in the flag, sorry. So there's your flag. One corner angle is 40, plus the other angle in the flag is Z minus X. And that is equal to the exterior angle. Right? There's it, there. And the exterior angle is that one. And you can see the exterior angle is the sum of these two angles, Z plus X. Okay. So we have this equation, 40 plus Z minus X. These are the two corner angles in the flag, equals Z plus X. And this is the exterior angle of the flag. We're using the exterior angle theorem. And now you can see the Z's cancel, this plus Z occurs twice. And the X's, if you take it to the other side, you get X plus X, which is 2X. 2X equals 40, and X equals 20 degrees. So this is a very nice result. It's not easy to prove or to calculate, but you can see we are using isosceles triangles here. We used it twice because we got two isosceles triangles, and we use the exterior angle theorem, right, with good effect, and we calculated X. Okay, now I have actually written out this proof in the way it should be done. Okay, what I'm going to do for the most part here is talk about a result and just write down things on this blank sheet, on my sheet, but I will give you the actual proof in detail, like the way I'm doing here, so you can have a look at it at your own time. You must know how to write out the proof. In the end, you have to write it out in a very logical way. I'm not going to do this one or any of the other ones. You can study all the way we write it down and learn how to write it in a logical way, starting from what is known and what is given, and go on to prove it. So the way to prove results that you're asked to prove is to use the given information and also use the theorems that we know, and you use the given information plus the theorems that we know or the axioms that we know, and in a logical way, step by step, we eventually come to the solution of the problem. All right, so that takes me to the next problem, which is this one. Right, it says a rectangular sheet of paper with sides √2 has been folded as shown. Okay, now we haven't actually, you can't see the paper here, but let me draw what the paper would have been originally. The paper would have been like this. There was a rectangular sheet of paper, just like an ordinary A4 paper. Right. And it's a rectangular. So what has happened is, it says here, this sheet of paper with sides √2 and 1. So the 1 is here. So the other side would have been square root of 2. So this is, so the sides of the rectangle, √2 and 1. There it is, a rectangular sheet of paper with sides √2 and 1 has been folded. So this part here has been folded like this. This is a crease of the paper. And that is what we see here. We see the folded part, but this corner is brought to rest on the opposite side like this, so that one corner meets the opposite long edge. And so you got, all you have is it's a rectangle and it's folded like this. You know what the sides are, and you're asked to calculate this length here. What is the remaining fold? You know, when you fold it like this, where must you fold it at so that this piece, this point here, goes directly to the top? So what is D? So the problem is to find D. Okay, I don't know why I'm using, let's just take the red out and use the black. Okay, so that is the problem. So what can we see here now? Let's go slowly with this. Now, even before we do that, maybe we should say something about the theorem of Pythagoras, right? Which all of you should know. It's a very important theorem in geometry. It says that if you have a right-angled triangle, a right-angled triangle is a triangle where one of the angles is equal to 90 degrees. Right? One of the angles is equal to 90 degrees. And of course, 90 degrees is a nice angle. It's a half of a straight line. Right? Then you have this very nice result that the two sides which contain the 90 degrees, there's your 90 degrees, the two sides which contain the 90 degrees, if you square each side and if you add them, then you're going to get the square of the other side, the third side, which is called the hypotenuse. The hypotenuse is opposite the right angle. It happens to be the largest angle side. Well, so the square on the hypotenuse is equal to the sum of the squares of the other two sides. So that is the theorem of Pythagoras. Pythagoras is credited for proving this theorem, but the other Eastern cultures, China and India, knew of this theorem long before Pythagoras. It's been now established. Okay, but anyway, the name has been given to Pythagoras. Okay, now the question is, how do you find this D? All right, now you can see since we folded this thing like this, so this line here is actually equal to the same as that, right? Because it's folded to sit on this. So we wrote down root 2 already. So in this triangle here, you'll see CFG, you have a right angle triangle and you know two sides. The nice thing about Pythagoras' theorem, if you know any two, then you can find the third. That too you can find, any two, because you have an equation which links the three sides. So if you know any two, the third one can. So yeah, in this case, you can work out the third side in this case is FG. In this right angle triangle, you get 1 FG. So what do we have? 1 squared plus FG squared is equal to the square root of 2 squared, right? The two sides, sum of the squares of the two sides is equal to the square on the hypotenuse. So when you square the square root of 2, obviously you're going to get 2. So it means that 1 plus FG squared is equal to 2. So FG itself must have been 1. So we can put a 1 here. Okay, now the moment you got FG is equal to 1, then you see now this right angle triangle now becomes an isosceles triangle. Because this side equals 1, this side is equal to 1. So two sides of this triangle are equal. So what does it mean? It means that these two angles are actually equal. The angles opposite the equal sides are equal. And now you can actually calculate this x because you got the three angles of this triangle are x, x, and 90 degrees. Remember, it's a right angle triangle. It's one of the angles of a rectangle. So you got 90 degrees plus x plus x. When you add those three angles, you are going to get 180 degrees. So if you bring all the x's to one side and solve for x, you will have that x is equal to 45 degrees. So now we actually have the x, right? You have the x, and that is 45 degrees, which is very nice. Right. But remember, this part here, this angle here was folded to come to this point. So this angle here is 90 degrees also. It's the same angle. It came down to this point here. So now you have two angles here next to each other. So you should be able to calculate this one, because when you add these two and subtract it from 180 degrees, you can get 45 degrees. You can see it straight away because one angle is already 90. So the other two angles will have to add up to 90. It's a useful fact. When you got one angle sitting on a straight line which is equal to 90, the remaining two angles will add up to 90 also. If this is 45, that has to be 45. But then you got that this is a right angle triangle also, because we started with a rectangle, and you got two angles of the small triangle here. If this is 45, this is also 45. So you can see how we move from one to the other, just using the results that we know already, the isosceles triangle, the Pythagoras theorem, right? And we come to this point here, and now we know the two angles are equal in this triangle. And we said if two angles are equal, then the sides opposite them must be equal. D is opposite 45 in this, and that other angle, the side opposite that is this. So that must be equal to D. Okay, and finally we are asked to find D, and this is very nice because now you have that this side here, D plus 1 is the side of a rectangle. But we know that's equal to square root of 2, right? Which is equal to the same as that. And then you got one equation with one unknown, and you can solve for D, take the D to the other side, and you have this nice result that D is equal to the square root of 2 minus 1. Okay, so I did a lot of talking, and as I promised you that I'll give you the full statement, the way you write this thing down, the way you write it down, and so the answer we got is square root of 2 minus 1. That solves the problem because we were asked to calculate D. And here is the promised proof that I right. So you can see I've written the whole thing out in detail, and eventually you got d is equal to square root of 2 minus 1. And please study this. You can see it's very systematically goes from one to the other, which I said in words, and you must be able to write it down in that logical way. After reading this, you put this, everything away and you rewrite it in your own words. You have to learn how to write geometry. Okay? Actually, the way you do it in school, I haven't done it in that same way. Because in school, you will write a statement, and in brackets at the end of the line, you will give the reason for the statement. I've given it here as a story, but you can rewrite it with just statements and the reasons in brackets at the end, and it's really the same thing, but I've written it out in greater detail. Okay, so we go to the next problem, which says that so problem number 3 states that A, B, and C are distinct points on a straight line. You can see there's A, B, and C. With AB equal to AC equal to 1. So let's put that down here. These lengths are actually equal to 1. So we normally, in our diagram, we put down the information that is given in the diagram so you can see it clearly. So these two sides are equal to 1. The square ABCD, so this is a square. All right, so that's very important. Just remember now, a square, all the angles are 90 degrees and all the sides are equal. So just bear that in mind, the back of your head, that all the sides of the square are equal. And it's also said an equilateral triangle ACF, ACF. So this triangle here is equilateral. So I told you earlier on, that means that all the sides are equal and all the angles are also equal to 60 degrees. So just remember that. Okay, so these are drawn on the same side of BC, and you have that this line here and that line are drawn and they cut at G. And the question is, what is the size of angle EGB? Now let's have a look at what EGB is. EGB. So the side that you're looking for is this one here. Let's call it X. So the question is, what is X? EGB. All right, somehow you have to use that the sides are all equal, and you also have to use the fact that this is a square and this is an equilateral triangle. Okay, now it turns out that we actually have to perform do what we call a construction here. You have to draw something which was not there in this picture, because if you try, you can try to work out X from the given information, and I think you're going to find it quite hard. You're going to find it quite hard. All right, so you'll always find that you need to find this angle here, and you can't do that straight away. But if you let's have a look at X. Can we find X? You will see that X is actually an exterior angle. You see this angle here, It's next to it. And this angle here is an angle in a triangle. If you go down this line, you come to B, and if you go this line, you come to C. So X is an exterior angle of this triangle here, BGBA. If you want to see the flag, go down, see, come down like that, go down, and you see that X is equal to the sum of two angles, which we can call Y and Z. So X is actually equal to Y plus Z. And in brackets, you will put exterior angle theorem. If you, in school, this is how you do it. Y is X. In fact, you'll have to write it in full now. They will tell you, in triangle GBC, X is, X is the exterior angle or whatever. All right, so at least we got a starting point. So now we need to work out Y. Now Y, you can see it's one of these angles, it's an angle here. But remember, this was an equilateral triangle. And this is 1. So therefore, all the sides are 1. And if you look at this angle Y, it's an angle in that triangle there. F, Y, how is Y created? F, B, A creates the Y. So you go back to that and you get Y is an angle in this triangle that I'm illustrating. But this triangle is isosceles. You see, these are both equal to 1. So it means that angle there is equal to 1. Y. All right. Because it's an isosceles triangle. Two are equal to 1. But now, sorry, we had load shedding. Let me just rewrite this. Okay, what I had here was, I had a Y here and I had a Y here. Okay, and all these sides are 1. Okay. And the problem was to find EGB, this one here was X, and we know that X is equal to Y plus, and we had that Z there. Now, if you look at Y, you got Y, and you got, there are two, this is triangle AFB is extended, right? So you have another flag here. There's starting from here, going up there and coming here. So the sum of the two Y's is equal to the exterior angle of this triangle here. You're going up like that, like that. So it's equal to that angle there. But remember, you got an equilateral triangle, yeah? So this angle, we know what it is. It's 60 degrees. So 2y is 60 degrees, so y must be 30 degrees, right? So I can replace the y by 30 degrees. This y. So let me put the 30 degrees there so we know what that is. Okay, so the only thing we have to do is to calculate z. But if you look at z, it's made up of that line and that line. So it's an angle between these two lines. And these two lines form a part of a triangle, this triangle here. And z is an angle in that triangle. But this triangle here is also isosceles because this is 1 and that is 1. But you have a right angle here. Then this is a square next to it. So you got a triangle whose two sides are 1, and the angle between the two ones are 90 degrees. And as we saw earlier on, we saw that the remaining angles will have to be 45 degrees. So the Z in this triangle is in actual fact 45 degrees. So we can put Z equal to 45 degrees. And there it is. You got Z is equal to 45. You got Y and Z are 30 and 45. So the X that we're looking for is 75 degrees. So guys, you can see the power of just the equilateral triangle, the isosceles triangle, and so on. And we are using those results repeatedly to calculate things. So that's one of the great things about geometry. You can calculate them. So even this unknown angle here, we can calculate it, X, right? It turns out to be exactly 75 degrees. And as I promised, we have written this thing out in full. And that is the way to get to 75 degrees. All right. So let's get on to the next problem. The next problem is number 4. It says here that 5 squares labeled A, B, C, D, E, or you can see them. So all these are squares. Right? So that's useful. All the sides are equal here. The same with B, C, D, and E. But they're all sort of one on top of the other, as it were, each touching the next square vertex as shown. Square B as area 20. So you know the area of the square, the area. Okay, let's just put that information in. So we'll just put B. B equals 20. By B, we mean the area. So let's abuse the notation. We said B was a square, but we can say B is the area. So the area of this is 20. Now, area of a square, remember, right? There's a formula for it. This area of a square is side times side. So it means that if you multiply the sides, the two sides of this square, you're going to get 20. So each side will then be square root of 20. So that's useful to know. Okay. Square C as side length 4. So square C, a side length 4. So in other words, the side length of all these is 4. Okay. So I use the next piece of information and I put it into my picture so that I can see what is said there. Square D as double the area of square B. Now square B is 40 and square D, there's D, its area is double. So in other words, this is area of D is 40. Area of the square here is 40. That's double. And now the question is, what is the area of square E? Okay, so that's the question. And to find the answer to that question, I evidently have to find a side of square E. And if I got the square side of square E, then I'll simply square that side to get the area. Before we proceed with the squares problem, which I described earlier on, we need to say something about congruence. There's a lot to be said here, so I'm going to go rather briskly. So if you look at the diagram in front of you, you will see a triangle ABC, and it's got three sides, A, B, and C, we normally name the angle, the side opposite angle A, a small a, and the side opposite angle B, a small b, and the same with angle C, right? Now, every triangle, this is very important, every triangle has got 6 numbers associated with it, the 3 angles and the 3 sides. Now, the beautiful thing is that if you know just 3 of these numbers, you can calculate the other 3 numbers. If you know only 3 of these numbers, you can calculate the other 3 numbers. You are not told how to calculate them at this early stage, but when you go on to grade 11 and grade 12, you will learn much more about that. So the question is now, which 3 numbers must be known in order to, what we say, determine the triangle completely. In other words, that from those, the triangle is completely known, right? Okay. So let me just go to the next slide. Okay, there are several cases. You can see this slide is rather populated, but let me start at the top here to explain what's going on. You see, here you got two triangles. I've named them differently, A, B, C, and D, A, F. You got 2 triangles. They've got the same sides, right? You can see one stroke. That means that those 2 sides are equal. AC equals DF, and BC equals EF. So here you've got 2 triangles which have the same sides. In other words, the 3 sides of one triangle are equal to 3 sides of another triangle. You can conclude that the 6 numbers are all equal. And if you look down here, you will see I've got, you take this remaining numbers is angle B, if I call it X, then X is going to be equal to one of these angles. And if you want to know which one, you will say that this angle here, X, is paired with double stroke, as you can see here. Paired with double stroke, X is paired with double stroke. So here too, the angle which is paired with double stroke is X, right? So likewise, the Z, if you take this angle, is paired with single stroke, so it'll be equal to that. And likewise, the third one. So if 3 sides of a triangle are equal to 3 sides of another, then all 6 numbers are the same. The 2 triangles are congruent, and all 6 numbers are the same. This is a very important conclusion. Given this, you can conclude that, right? And this congruence is used many, many times. These 2 triangles are identical. The word congruent means they're identical. If I cut this triangle out, I can place it exactly on this, right? Okay, so that's the first condition. 3 sides. You call this 3 sides. Okay? And it's normally written as SSS, right, in an abbreviated form. Now here, you have 2 sides. You notice this, nothing is said about the third side, but you know this equals that, that equals that. But you got these 2 angles are equal. So you've got 2 sides of one triangle equal 2 sides of the other, but the angle between them, you can see these 2 sides make up a new angle between them. It's called the included angle, and we put that between the 2 S's to show that the angle between these sides is equal to the angle between these sides. So if you have these 3 conditions, 2 sides and an angle, but it must be an included angle, then all 6 numbers are the same. All right? And likewise here, you've got 2 angles and a side. Right? We say 2 angles and a corresponding side. So you can study this and see what we are saying here. Those 2 angles must be nicely located in the same places. Like here, this is not the same as that. And as long as you have that, then these 2 triangles are congruent and all 6 numbers are the same. There is one exception to this 2 sides and an included angle. You see, in a right angle triangle, you can have the hypotenuse and the and a side, and the included angle, you need not have that equal. But if you've got a right angle, a hypotenuse and a side, right, then the triangles are congruent. And it's an exception to that. So in one case only, the angle need not be included, and that is when the angle is a right angle. All right, so with that background, we can now go on to the squares problem. Okay. Okay, so here we were asked to find the area of E, and we are given that the area of square B is 20. Area of square B is 20. And it is also given that side C, square C has got length 4. All the sides of the square are all equal, and they're all equal to 4. And the area of B is 20. And this, we are also told that D has got double the area of square B. So the area of D, the B is 20. So the area of D will be, the area of D will be 40. And the question is, what is the area of E? Right, now, listen carefully. To find the area of E, we will know what the area is if we know the sides. So we don't know the side of E, so let's call it X. Right, so we don't. So our goal is to find X. Okay. Now, I want you to have a look at this triangle here and this triangle here. I claim that these triangles are congruent, that they are identical. If you cut this triangle and put it on there, they will fit. Right, now how do I know that? Do I have 3 things of this triangle equal to 3 things of the other? Well, for one thing, this is a square, so that side there will be equal to that. Okay, so it's 1 down, 2 to go. And we also know that this angle here is equal to this angle here, because these are 90 degrees. All these are squares. So you've got one side and one angle, right? 2 down, 1 more to go. Do we know anything else? And the answer is yes. Now watch. If you look at this angle here, this is the tricky part. It's equal to 90 minus this angle here. Let's do it in a different way. Let's give a name to this angle. Let's call this angle Y. Let's call this angle Z. All right. So what is Y plus Z? Y and Z are 2 angles of a right angle triangle. The other angle is 90 degrees. So Y plus Z will be 90. But if you notice this angle, this is a square here, so that is, and Z plus W, these 2 angles also add up to 90 degrees, because this angle here is 90 degrees, and all 3 are sitting on a straight line. So W plus Z will also be equal to 90. So what does this mean? That Y plus Z is equal to W plus Z, which means that Y is equal to W. So this angle here is actually equal to this angle here. And I've just proved it. In place of Y there, W, I can put Y. Or otherwise, a little curl like this to say they're equal. So now you've got 2 angles and a side of this triangle equals 2 angles and a side of this triangle, which means that they are identical in every respect. Now, in particular, this side here will be equal to one of the sides here. Right, now which one? This side here is opposite angle Y. The side here is opposite angle Y. So therefore, this side is But we know that this side is 4. And it's equal to, so one of these sides is 4, and the side which is 4 is the side in this triangle which is opposite y. It's squared off. So this is 4. But now we know the side here because the area of this is 40. So this side squared is equal to 40. This is a square. So when you square this side, you're going to get 40. So the side itself will have to be square root of 40. Right? To get 40, the number which is squared, the number which needs to be squared to get 40 is square root of 40. So this side here is 40. So now in this right angle triangle here, I've got two sides. I've got square root of 40. Let's just isolate the triangle so that I'll take it out of the complicated setup there so we can see what's going on. So we have a right angle. I'm rewriting this triangle here. This is unknown here. And this is square root of 40 because it's equal to the side of the square. And we just saw that this is 40. We needed to find not necessarily x, we needed to find the area of square E. So we need to find not just x, but we needed to find x squared. All right, so x squared is, that's what we needed to find. But now, from Pythagoras, we've got that x squared plus 4 squared. We've got two sides is equal to square root of 40 squared, which is 40. So if you've got two sides of a right angle triangle, you can find the third side. So x squared is equal to 40 minus 16, which is 24. And that is exactly what we needed to find. X squared, not x, but x squared. So the answer, the area of E is x squared. So that is 24, because we just calculated it. Okay. So I'm going to leave this picture here with you so that you can see exactly what the arguments were eventually to get the area to be 24. Okay, so let's get on to the next problem. Problem number 5. Problem number 5 says ABCD is a rectangle. Right? All the angles are 90 degrees, in other words. And P is an arbitrary. Arbitrary means any. Right? No specifications, any point or random point. So P is, we just chosen anywhere in its interior. That means in the inside. Calculate PA. PA, because we don't know what PA is. So let's give a name to it. Let's call it X. Calculate PA in terms of PB, PC, and PD. In other words, the remaining three lines. Okay, let's give names to these. Let's call them B, C, and D, because this is going towards B, this is going towards C, and that's going towards D. So we calculate P in terms of. So what does that mean? I need to write out, get X equals, and I need to have only A, B's, and C's here. Some expression, whatever it is, A plus B minus C or whatever, X equals something which involves only A, B, and C. Right. Now, this is not an easy problem. The way to do this, as it stands now, we can't do it. But there is a way of doing it. And the way to do this is to create, through P, you draw a vertical line and a horizontal line. Okay, so through P, you draw a vertical line and a horizontal line. Okay. And now we need to calculate x. Okay, what I'm going to do is now I've got lots of right angle triangles. So what we are going to do is choose the right angle triangle several times. Okay, so let's give new names. So in this triangle here, x, I've got it's equal in this right angle triangle. This one here, I've got x as hypotenuse. Okay, let's give new names now. We'll call this P and Q. So we have x squared is equal to P squared plus Q squared. Right. Now this is a rectangle, so this is Q also. And this P, this is the same as P here. Okay. So now let's look at this rectangle here. Okay, we got two sides. Let's give another name. Let's call this R. So now you got B squared from this rectangle, B squared, you got P squared plus R squared. Okay, so if this is R, this is also R, because this is a small rectangle here. But I don't have this one, so let's call this S. So C squared in this rectangle here, so C squared is equal to S squared plus R squared. I want to use Pythagoras many times. So if this is S, this is also S here. And then finally, you got D squared. D squared is equal to S squared plus Q squared. And so now you got four equations then, lots and lots of unknowns. And it's quite frightening. But if you look now, you'll see here, I've got P squared, Q squared, R squared, and S squared, these two, right? So if I add these two, I'm going to get P squared plus Q squared plus R squared plus S squared, right? So I've got X squared plus C squared is equal to P squared plus Q squared plus R squared plus S squared. But then, when you add those two, you're going to get the same. This two, when you add these two, you'll also get P squared, R squared, Q squared, S squared. So you got P squared, Q squared, R squared, and S squared, even when you add these two. And that's the same as B squared plus D squared. Right. So in short, you've got X squared plus C squared on the extreme left equals B squared plus D squared. So that gives you X squared in terms of it's B squared plus D squared minus C squared. Actually, we needed to find X in terms of B, C, and D. That's P, A, P, C, P, D, B, C, and D. And this is exactly what I've got. So X squared is equal to that. So that solves the problem because X itself will be equal to the square root of that. So it's a rather complicated looking problem because there are so many unknowns here. And to solve this, you can't solve it as it is. You have to perform this construction to create four rectangles. See? And you use the Pythagoras theorem four times, right? As we did here. And then that will lead to the answer. Okay, and as I told you earlier on, I'm going to give you the full solution so you can have a look at it at your own time. And I've got some other symbols here instead of B, C, and D, but it's the same principle. Okay, we go on to problem number 6. Problem number 6 says that 50 points are chosen inside a convex polygon having 80 sides. All right. So we need to know something about polygons. So let me pause here and tell you a little bit more about polygons. So before we proceed with this problem, let's just say something about polygons. um, oh, just ignore these numbers here. I'm sorry about this. The sum of the angles of a polygon having n sides is 180 times n minus 2 degrees. This is a very, very important formula, right? Just remember that if a polygon has got n sides, you reduce the number of sides by 2 and multiply by 180. That number will give you the, if you add up all the angles of the polygon, you will get that number of degrees. Like for instance, now what's a polygon? A polygon, these are examples of the polygons. I've got 4 examples of polygons. It's a figure which is bounded by straight lines, all straight lines here. And triangle is the simplest of all polygons. It's got 3 straight lines. So here, the n is equal to 3, because n is the number of sides. And if you reduce 3 by 2, you get 1. And 180 times 1 is 180. And you know that if you add the angles of a triangle, you're going to get 180. Right, so it verifies. Yeah, if you take a quadrilateral, if you add up all the angles, what do you get? Well, n is equal to 4 in this case. 4 minus 2 is 2. So it's 180 times 2, which is 360. So if you add the angles of a quadrilateral, you're going to get 360. Likewise, if you take a hexagon, which is a 6-sided figure, you're going to get 720. And if you have a 7-sided figure, you're going to get 900. That is, the angles add up to 900 degrees. So that's an important formula. Now we can go on to our problem. It says, you've got a polygon. I've tried to draw the polygon here because it's got 80 sides. I cannot draw the polygon with 80 sides. So I've just drawn a few points, few vertices of that polygon. And I'm saying it goes on, and we not, obviously we are not going to draw all the sides. But we just illustrated here, then there are 50 points which are chosen inside that polygon. So inside the interior or the inside, 50 points are chosen. And the polygon is cut into triangles like this, right? So that you don't have any triangles which are cutting each other. Right? And the vertices of the triangles are just those points which we got, those 50 points and those 80 vertices of the polygon. If it's got 80 sides, it means it's got 80 vertices. So you got the triangles, their vertices are just amongst those 50 and 80 points, which are already there. And the question is, how many triangles are there? It'll be almost impossible to actually draw this thing and count all the triangles. So there must be some way of doing this. An interesting problem. I took just a case of where we have 6 sides. So here we have a polygon of 6 sides, and the number of points that we have chosen inside there, this thing has 6 sides. And I got 1, 2, 3, 4, and 4 points. And I try to see how many triangles there are, because the question is, if you've got 80 sides and 50 points, how many triangles are there? I've got 6 sides and 4 points, how many triangles are there? I actually, to count the number of triangles, what I did was I counted all the angles in this picture, and I numbered them, as you can see, and I found that there were 36 angles. And therefore, each triangle has got 3 of those angles. This is the 3 here, the 3 here, and 3 here, right? So therefore, there are 12 triangles. But obviously now we can't draw all those angles like that. So there must be some other way of solving this. So we employ a very nice trick here. What we do is add all angles. This is all the angles that you can see in the picture. In this picture, you got 36 angles. Add all the angles. Right. Now, there are 2 ways of doing it. One is at each point, if you add up all the angles at each point, you're going to get 360. So all those angles there add up to 360. Here too, the 3 angles here add up to 360, 360, 360. So there are 4 points, and they all add up to 360 degrees. Right. So the interior points, those will be that. But what about the others? You see, the rest of the points will be all at the vertices. Okay? All these angles. So if you add up all those angles at the vertices, then you got exactly what I told you earlier on. This is a 6-sided figure, and that gives you the sum of all the interior angles of the 6-sided picture. And I told you it's 180 times 6 minus 2. 6 minus 2. So this gives you all the angles. If you add up the whole lot of triangles, if you add them up, all the angles, this is what you'll get. But look, suppose we don't know how many triangles there are, right? So let M, I use the symbol M for the number of triangles. That's what the question is. How many triangles are there? And when you add up all the angles, you're really adding up the angles of M triangles. That's another way of doing it. There's the 3 angles of this, 3 angles of that, 3 angles of that, and so on. And when you add the angles of M triangles, each triangle is 180. So the sum of the angles of M triangles is 180 times M. So there it is. You have one equation with one unknown, right? And you notice that you got 180 times M. Sorry, this writing is not nice at all. So I apologize for the messy. All right, so if I divide right throughout by 180, you 4 times 2, which is 8, and 180 times, I'm dividing by 180, so you just have 6 minus 2, and that is equal to M. So M is equal to 12, right? And if you count the number of triangles here, you will actually see that you have 12 triangles. Well, in any case, you have 36 angles, so each triangle has got 3, so there are 36 over 3, 12 triangles. But if you do it like this, now it's very complicated, because you've got 80 sides and 50 points. So in general, this thing here is in general. Here you have, okay, no, this is when you have 6 and 4. So in the same way, when you use our problem here, uh, all right, so I'm going to show you what we've got. When you got 50 points inside the polygon, which has got 80 sides, so this is what you have here. And when you calculate, right, so let M be the number of triangles. The sum of all the angles of the triangle is 180 times M, right? When you add you got 80 sides, the total number of interior angles, if you add up all the interior angles, with 80 sides, n minus 2 is 80 minus 2 times 180. That gives you all the angles at the vertices of the polygon. And at the points inside the polygon, there are 50 points and there are 360 degrees at each point. So if you add up all the angles at those 50 points, you're going to get that. If you add up all the angles at the vertices, you're going to get that. And that is the same as adding up all the angles of M triangles. So you've got a very nice equation here. If you divide by 180 right throughout, you will simplify and you get the problem is solved, because then you have 178 such triangles. Okay. So let's get on to the next problem. Let me see, I'm not sure whether I got enough time. So I'm going to just move on to something else. If I got time, I can come back to that. Let's have a look at this. This looks like an interesting, I'm not sure what's going on here, but this is a game. So I've decided to also add a different kind of a thing to this geometry session. This is not really geometry, but we'll try to solve some problems involving games, where two people are playing a game, and with logic, you'll be able to answer some questions. Like in this particular question, you got Zola and Ron play a game by alternately moving a single 10-cent coin on a circular board. So what these people have is a coin. So it's a coin like that. Okay, so imagine this is a coin, and Z stands for Zola. Zola plays first. So she can take this coin and she can move it that way or that way or that way, any way she feels like. And then after that, a partner called Ron, maybe Ronald. So Ronald, he then takes wherever it goes, he makes a move. Right? He can go in any direction, but you must not go to a square which has already been used. That's the rule. All right. So he goes to a new square, and well, not new square. This is a new region. These are all sort of regions here. And Zola does the same thing, and they keep going, right? But the big rule is you're not supposed to go back to a square which has already been occupied before. All right. The question is, the last person who is able to move wins the game. In other words, once you move and the other person finds that he or she cannot move at all, because no matter which way you look, the squares are already occupied and had been there before. So the last person to move wins the game. Right. Now, you got Zola plays first. It says here Zola plays first. Now, they say which player can play in a way that guarantees a win by him or her. All right. So there must be some strategy. Now, how are we going to solve this problem? Okay, so you need to have all the squares occupied except the last one. So let's have a look at the last one. When I put a Z here, it means uh, the player starts with the 10th set game marked Z on the board. So Z is this, that means it's Zola's play. When you've got the Z there, it means it's Zola's play. So what does Zola do? You see, you get cramped up in the low, right in the middle, right? So imagine, suppose Ron got in, suppose Zola got into this, into one of these squares here, right? So for the first time, suppose Zola got in there. And suppose you can't go outside, all of them are full. Or a player, or there's another condition. A player may move either clockwise, one position, or one position towards the center. So you can't go backwards. You can either move clockwise, go down like this, or move to the center. Can't go backwards. You can't go anti-clockwise. You can either move clockwise or move toward the center. Okay. So suppose Zola eventually moves in here, right? Now, it can't go backwards. So Zola can only move clockwise, right? So it is Zola's turn, and Zola moves to this point here, clockwise, right? And now it's Ron's turn. And then Ron moves to this, and it's Zola's turn. And Zola moves to that, it's Ron's turn, and Zola, and Ron, and Zola, and Ron. Now Ron was the last person to play, and now Zola can't move because all the places are occupied. So the moral of the story is that when Zola is the first to enter this circle, the inside circle, then Ron wins. So Zola will have to play in such a way that she is not the first to move. She'll try to force Ron into the center. Because once she forces Ron into the center, then um, then she will definitely win the game, as we've just seen. Okay. So what does Zola do? She just moves. She doesn't move toward the center. She tries to avoid moving to the center. Oh, well, actually, she can move toward the center. Suppose in this case here, Zola can move here. So the strategy is Zola moves, doesn't go toward the center. She must try to avoid going toward the center. So she goes here, it's Ron's turn. And Ron, if Ron is wise, Ron will also try not to go toward the center. He will stick to the outer region. Now it's Ron's turn and can't go in there. So Ron has to go inside there. Now it's Zola's turn. And then Zola carries on. Comes here, and again it's Ron's turn. And Ron is forced to go inwards. And then now it's Ron's turn. So Ron now moves towards the center. Now, as we see, when Ron moves towards the center, now it's Zola's turn, and Zola will win the game because Ron was the first person to move towards the center. Okay, so that's the strategy. Okay, yeah, this is a game, and you have to sort of figure out what happens to at the end, and then work backwards to realize what needs to be done. Okay, so that's an example of a game. The next one, let me show you the picture so that you have this available. Well, I've explained it to you already. There's no further picture to go there. Okay, let's have a look at the next one. Here, two opposite corners of an 8x8 grid are removed. This is an example of what we call a tiling problem. We'll come back to that later. So you got an 8x8 grid like this, and the opposite corners are removed. Now, here's an interesting question. You can try this with people. You've got 62 squares left, and you have 31, because there are 64 squares originally. 2 have been removed, so you've got 62 squares. You've got 31 1x2 dominoes. You call this dominoes. You've got 31 of them. Now, the question is, can you place the dominoes on the grid in such a way that all 62 squares on the grid are occupied? Now, you can try this. Try to do this. Take this, and put a grid here, and put another grid there. The 2x2 there, or there, or there, or there, or whatever, and see whether you can occupy the entire lot, all 62 squares, right? You can try, and you try quite a few times, and even if you try maybe 50 times, so you still don't know whether the next one, whether you'll be able to get it, right? So you have to keep trying until you get it. Now, the fact of the matter is you can try until you die of old age, but you'll never be able to do it. So that's a very interesting statement. The question is, how do I know? How do I know that this is impossible to actually do? You cannot fill these in this thing here. Now, here's the beautiful solution to this problem. How can you prove this? The way to do this is to color this thing as if it's a chessboard. All right. Now, a chessboard, this is what I've done. A chessboard normally, okay, suppose you've got a black square here, white, black, white, and so on. Now, you'll notice that along this diagonal here, you got 2 black squares have been removed, right? Opposite corners have been removed. So the 2 corners which have been removed have the same color. Okay, when you put it alternatively like this, it's easy to see. So they got the same color. So in other words, you got more whites than black. Originally you had 64 squares. And then when you colored it as a chessboard, you had 32 white and 32 black. Now, 2 have been removed, but both of them are black squares. So now you got 30 black, and the white squares remain intact. And that makes your 62 squares altogether. Right. Now, when you take a domino and you place it on this thing, it should be quite clear that it will cover 1 black and 1 white. You cannot have a domino covering 2 of the same color because it's a 2x1, right? So if I place 31, if it is possible to cover up all these things, then it means that the 31 dominoes will cover 31 white and 31 black. But you don't have that scenario on the square, on the chessboard. You don't have 31 blacks to cover. You only got 30 blacks. See? So if you make the assumption that it can be done, then you have this situation, and you know that this is impossible because these 31 dominoes cannot cover 31 blacks because there are only 30 blacks altogether. So it's a beautiful solution to a problem which people will try practically, and they will suffer and suffer and struggle, and they will not be able to do the problem. And we have shown mathematically that it's impossible to do it. A very beautiful way of showing it's impossible. And the way to prove this is you assume it is possible, and then you come to a situation which is untrue. And with the moment you do that, then you say, well, what went wrong? And what went wrong was that the assumption that I made is false. So the assumption we made is, suppose it can be covered, and that is now false, and therefore what is true is that it cannot be covered with 31 dominoes. All right. The next problem is very similar. Okay. This time you got to think like this now. You haven't got dominoes. You got a block which has got four squares like this. Now, and you got a 10 by 10 grid. So you got 100 squares altogether, right? Can this be covered with these tiles? With these tiles shaped like this? Is it possible to cover the whole lot? Well, again, just like before, we can prove that you cannot do it. Okay? And how do you go around proving it? Well, you've got 100 squares here, and again, you tile this thing like your chessboard, right? You tile this thing alternate colors, black and white, black and white. We're calling it tiling it, because it looks like a tiled floor. So that's why this is an example of a tiling problem, right? So you do the same thing that you did before. That will help us to solve the problem. And suppose it can be done. Again, you're assuming the impossible here. Suppose it can be done, then what happens? You've got these each one has got 4, and you got 100 squares altogether, right? So it means if it can be done, suppose it is possible to cover this entire board with those 4 tiles, right? So how many tiles are used? Well, each tile has got 4 squares, and you got 100 squares altogether, 10 by 10. So you would have used 25 tiles. All right. Now, those 25 tiles, they cover this. But notice that each tile if you color this thing like the chessboard, right? Each tile covers 3 white, well, in this case, in the example that I've shown, it covers 3 blacks and 1 white. We'll call it 3B plus 1 white. Or I could have had 3 whites and 1 black. All right, so we don't know. When you put the thing, this is what happens, right? But with the very shape of the tile, that's how it has to be. So you don't know how many of these types. Suppose you got M of this type, and suppose you got N of this type. By type, I mean M tiles which cover 3 blacks and 1 white. So how many blacks altogether? Oh, okay. This means that if you got M of one type and of N of the other type, so they will add up to 25 because you are covering up the whole thing, right? Okay, now let's just count the number of blacks that are covered. So you got the M tiles cover 3 M blacks because each M covers 3 blacks and each N covers 1 black. So there are 3 M plus N blacks covered. And likewise, you will have M plus 3 N whites covered. But I'm making these equal because the number of blacks is equal to the number of whites. You got a 10 by 10 board, and you will have exactly 50 blacks and 50 whites when you cover it like this. So you got these two, the number of blacks covered will be equal to the number of whites. When you solve for this, you get 2M equals 2N, and you get M is equal to N. Right, so therefore M is equal to N. Right. But then you will have that M equals N. So if you solve for M, you get 12 and a half, which is impossible because M is the number of tiles of a certain type, and you can't have 12 and a half such tiles. So we come to a contradiction. Right? If it can be covered, we find that the number of tiles is not a whole number. So therefore, our assumption is false. Therefore, it is impossible to cover this. Okay. Okay, this has been a somewhat long session, and I thank you for listening. And we will now close up this session. And I hope you enjoyed the session and you got a taste of geometry. I will meet you again in the last session to continue with geometry.